Okay, we can start. Okay, so today it's the last class of this course. We are doing the second part of the last chapter, chapter 5. I see there is some new student in the class, even if it's the last one. So, and for everybody, just to remind you, the first part of the chapter 5 from previous lecture. So what we have done, we have defined some paths, some weighted paths, and in a certain set, I have some fixed number of starting point, A1, A2, AK, fixed number in blue point B2, B1, BK. The weight of the path is the product of the weight of each elementary step, where the weight V of ST is any evaluation, any map from a pair of vertices to a commutative ring. And then I define the matrix, the K by K matrix, Aij, equals the sum of the weight of all the paths going from Ai to Bj. And then I am considering the determinant of this matrix. And under certain condition, which is called the crossing condition, then this determinant becomes the sum of the weight of all the configuration of paths. They are non-intersecting, 2 by 2 disjoint, and each path go from Ai to Bi. So this was the main proposition last time. And then we define binomial determinant. Binomial determinant is any minor of the Pascal triangle, where I put some 0 above the diagonal. And then by the main lemma, any binomial determinant is interpreted as the number of configuration of paths starting from this blue point, ending to the red point, with elementary step north or east. So such minor is always positive in the Pascal triangle. Then the second main proposition was in the case of all the starting points are consecutive, all the blue points are consecutive, then there is a nice formula for the determinant as a product divided by another product. Numerator, we introduce the contents shifted by A, and denominator, the hook length. Mu is a certain partition which is defined from the configuration of red points. And then we apply this theorem to enumeration of semi-standard Young tableau. So here is a semi-standard Young tableau. The number are increasing weakly in the row, increasing strictly in column, and the number of such semi-standard Young tableau is going to be the ratio of the contents of mu. Mu is exactly the same, but with a certain rotation. The content of mu shifted by A, and the content, the hook length of mu. So you have a nice, again, formula for the number of semi-standard Young tableau. It's a very classical formula. Sometimes it goes back to Philippol, sometimes to Stanley. Then we apply this in a special case of plane partition. Plane partition, such tableau where the number go decreasing weakly in row and in column. Plane partition are nothing but the coding of a 3D Ferrer diagram, where you have some cube. In each cell of this plane, you put a number of cube, which gives you the height of each column of cube, and you get a 3D Ferrer diagram. And we have a nice formula for such plane partition or 3D Ferrer, which are bounded in a certain box, A by B by C. And this formula is a McMahon formula. And we showed that there was a bijection between such plane partition and configuration of paths, like this. Then we add some new step to get binomial determinant. And then we apply the formula contents by hook length, and we get this formula. So now I continue the application of the main lemma to Jacobi identity for Schur function. So in previous lecture, we have seen very quickly in a complement about jeu de taquin and Plactic monoid. We have seen symmetric function, symmetric polynomial. So just a drop. It's a whole book. It's a whole lecture. It's a whole course on symmetric function. But you will have 10 minutes of an idea what is the philosophy of symmetric polynomial. So I take a polynomial in n variable, coefficient in a ring K, and it's called to be symmetric if for any permutation, when you permute the variable, the polynomial is invariant. So this is the space of symmetric polynomial in variable x1, x2, xn with coefficient in a certain ring K. So this was in chapter 4c. We talk about Schur function and Plactic monoid and symmetric polynomial. So there is some classical basis it's a vector space, and there is some classical basis for such a vector space. So one classical basis is defined from homogeneous symmetric function or complete symmetric function. So you take alpha, a composition of P. Composition means it's a partition, but the order of the part is important. If you don't take account the order, then you get a partition. A composition, it's a sequence of numbers, positive or zero numbers. So there's a sum equal to P, and you have the first one, second one, third one. So this is called a composition. And then for each composition, you take this monomial, and you sum over all possible composition, such that the degree of the monomial is going to be the sum of the alpha 1, alpha m, which will be P. So you fix the degree P, and then you have a sum of all such monomial, and this is called the homogeneous or complete symmetric function HP. And now I can define for any partition lambda, in part lambda 1, lambda k, then I can define the homogeneous symmetric function indexed by lambda, the product of all this homogeneous symmetric function. And this is well known that you get the basis of the space of symmetric polynomial with homogeneous. Then there is a second very classical basis, the elementary symmetric function. So elementary, you take the sum now over all monomial, but all the letters are distinct. All monomials such of degree P in the variable x1, x2, xm. This is a symmetric elementary function. Everybody knows this because it's when you have the root of any algebraic equation of degree n, then the coefficient can be expressed in terms of the symmetric elementary function. Again, if you take any partition, you extend this to have an elementary symmetric function indexed by the partition. And again, you get another basis of the space of symmetric polynomial. So in the previous chapter, we have seen another basis, the Schur function. I have defined it, usually defined as a ratio of two determinants, but a very practical way to define it combinatorially is to say that this Schur function is going to be the sum. So a Schur function is indexed by a partition in variable x1, x2, xm, and you take the sum of the weight of all semi-standard Young tableau of shape lambda with entrée 1 to m. So what it means, so here is an example. I have my partition lambda. I have variable 1, 2, maybe until 8 or until 10, I don't know. And you take a semi-standard Young tableau, means weakly increasing in row, strictly increasing in column. So what means the weight of the tableau? The weight of the tableau is a product over all the cell of x, index I is the cell. I of the cell means you replace I by x in this I. So in this example, the weight of this tableau is this monomial. See, you replace each of the number in the tableau. I is replaced by the variable x in Si. So here I have x1 to the cube because I have 3 times the 1, x2 to the cube because I have 3 times the 2, etc. So you fix the shape lambda, you take all possible semi-standard tableaux, you get a big polynomial, the sum of the weight of all semi-standard tableaux with variable, you have to fix the bound of the integer I. So you fix the bound, the value are between 1 and m, the value inside the tableau, and for a given m, then you have a Schur function. So it's not obvious at all from the definition that this function is going to be symmetric. But it's a nice way to define Schur function for combinatorics who don't want to make too much calculus of determinant. It's a direct definition using what you have seen in the class, semi-standard Young tableau partition. And then again, this Schur function gives you a basis of the space of symmetric polynomial. I like to call this a royal basis. It's really the royal basis. It's very, very useful in many For example, we have seen that from Lascaux that he used the Chern calculus of fiber bundle, etc. in algebraic geometry. He used the basis of Schur function to show that all the coefficients of pairing are exactly the binomial determinant. They are all positive, and they are exactly all the possible binomial determinants. So now I am going to translate into combinatorics homogeneous symmetric function. So first lemma, I can define as path, as weighted path. Homogeneous symmetric function is the sum of all Motzkin paths going from A to B, or left factor, beginning of a Motzkin path. Motzkin path, there is going up, going level, or going down. So the valuation when I go up is 1. When I am at level k, I put xk plus 1. So it reminds me some Motzkin path of the moment of orthogonal polynomial in the previous lecture. And I don't go down. Going down is 0. So the Motzkin path is always going at level or going up. So A, the starting point is 0, 0. Ending point is B equal P plus M minus 1 and M minus 1. And you see that any composition, you can always, to any such monomial, you can always define bijectively a certain path. Like this, with repetition of letters x1, x1 square, x3, x4, x4. So here p equal 5. So this is the maximal, this level is the maximum, is m, maximum possible is m minus 1, maximal possible value of the index of the variable, and you can have repetition of letters. So this is a visual interpretation of homogeneous symmetric function HP. Now I claim the famous Jacobi-Trudi identity is to say that the Schur function can be expressed as a determinant of single homogeneous symmetric function. In fact, the transpose of this. So how it works, see on the diagonal you have H5, 3, 2, 2 in this example. Each time you go to the right, you increase index by 1. Each time you go down, you decrease index by 1. And you start with 5, 3, 2, 2, which is going to be related to lambda. So in this example, I have lambda equal to 2, 3, 5. So lambda is this partition, 2, 2, 3, 5, which give me the ending point of the picture. So from this weakly increasing sequence, as usual, you associate a strictly increasing sequence. You keep the 2. You add 1 to the 2 gives 3. You add 2. 3 plus 2 equal 5. 5 plus 3 equal 8. So 2, 3, 5, 8 are exactly the coordinate of the ending point of the path. And I claim that starting from any of these points, A1, A2, A3, or A4, and ending in any of these points is exactly the coefficient in this matrix. Any coefficient, any homogeneous symmetric function, the term ij of this matrix is going to be exactly the sum of the weight of all the paths starting from AI and ending in Bj. So you see, you have to be careful on when you apply the LGV lemma in the way you number the points. I am numbering them from right to left, and here also from right to left, so that I get this matrix.
So, what is your Hij
is this? So first in the diagonal, you have a 5, 3, 2, 2, which is exactly 5, 3, 2, 2. So in the diagonal, the path going from A1 to B1, this path, if you go from A1 to B1, you have 5 levels, which means you are working with a homogeneous symmetric function H index 5, this one. Now this term is exactly with a monomial of 3 terms, so it's exactly the sum of the weight going from A2 to B2. See, from A2 to B2, I have 3 levels, I have 3 variables, so I get this homogeneous symmetric function. And the two other H2, H2 is when you go from A3 to B3, I have 2 variables. When I go to A4 to B4, I have 2 variables. So the terms of the diagonal are correct. Now when you take, for example, the path going from A1, this is A1 to B1, now A1 to B2, A1 to B3, so you have to show that this is increasing. So A1, maybe I am wrong, because A1 to B2 is the number is decreasing. So there is a mistake somewhere. It's maybe no. This is it's written the transpose of this. So A1 to B2 should be this. A1 to B3 should be this, and A1 to B4 should be this. So here I have only 2 levels. Here 0 level. So A1 to B2. If I go, you see, I will need only 2 variables. A1 to B3. Then I will have only 1. No, I will have 0. 0 variable, and then it's impossible, A1 to B4. So you can check that this gives you this. So each time you move left or right the starting point, you move left or right the ending point, you get this variation. Increasing number when you go like this, decreasing number when you go like this, but you have to take the transpose. And so my theorem is just, I get a proof, because the Schur function is nothing, the sum of the weight of this. So Schur function is the sum of the weight of this configuration. And this configuration is exactly the determinant of this. Each individual term is the sum of the weight of paths starting from one point, ending in one point, and this is a homogeneous symmetric function. So this gives you a proof. This is a geometric proof of this famous identity, Jacobi-Trudi identity.
Can you explain the relation between these two?
No, so the first, each row of this tableau is going to be in bijection with a path. So here there is the 1, 1, 2, 5. So the first path, 1, 1. Then I go to level 2, and then I go to level 5. So each row it gives you a path of this non-crossing configuration, 2 to 3. So I have to go to level 2, then level 3, and then I go to.
So the non-crossing
3, 5.
condition says that strictly increasing.
Yes. As usual, when you have a Young tableau, semi-standard Young tableau, you can encode by a path. If you take the row, you get some path, and to say that the column, to say that the paths are non-crossing, it's equivalent to say that the column are strictly increasing. Now we are going to do the dual. We are going to associate with such tableau some paths by taking the column, which are going to be strictly increasing. And then to say that the row are weakly increasing is equivalent to say that the configuration is non-crossing. So let's do it. So the dual, by taking a column instead of a row, give you now elementary symmetric function. So again, I claim that elementary symmetric function can be interpreted as the sum of such a path. Now the path, you can go diagonal with weight 1, or you can go north with the weight is the height of the path, of the step. x2, x3, x5, x8. Now I claim that if you put the B prime in good position to A prime, I claim that the sum of the weight of such path is exactly the elementary symmetric function. The height of the ending point gives you the m. How many variables you allow it? So x1, x2, x3, x4, x5, x6, x7, x8. And now because of the path, you have a monomial and all the variables are distinct. And you get, for each monomial, you have such a path. So there is a bijection between each monomial in the expansion of the elementary symmetric function and such a path. So the sum of the weight of all the paths, A prime and B prime are fixed, is the elementary symmetric function. Now I have a dual Jacobi-Trudi identity. I have the Trudi-Jacobi identity. The dual is just the Schur function is the determinant of this matrix, but the transpose of this. So in the diagonal, you have 4, 4, 2, 1, 1, which should be related to a certain partition. So here is a partition. You see, now I have the same partition as before. I have lambda equal 2, 2, 3, 5. Now I take the transpose, the dual, the transpose of the partition, which is lambda star, which is now by column 4, 4, 2, 1, 1. I am reading the partition by column 4, 4, 2, 1, 1, which give me the term here 4, 4, 2, 1, 1. The column of the partition gives you the index in the diagonal. So I have to find some path going from AI to BI, such that I get exactly the term of the diagonal, and then you see you increase by when you go right, and you decrease when you go down. So let's take the... Now you label the point from left to right, A1, A2, A3, A4, B1, B2, B3, B4. So the B, this B is in the coding of this dual partition. As usual, I transform this into 1, 2, 1 plus 1, 2 plus 2, 4 plus 3, 4 plus 4. So you have 1, 2, 4, 7, 8. And I put my point like this, 0, 1, 2, 4, 7, 8. So the ending point, this B, the ending point are fixed by the lambda star. Starting point are consecutive, as usual. And now you are encoding this semi-standard Young tableau by a configuration of non-crossing paths. So each path corresponds to a column of the tableau. So you see you have this path, for example, 1, 2, 3, 4. So the first, no, yes, this is the last column, x5. Let's take the first column, 1, 2, 3, 8. So you have 1, 2, 3, and then 8. So you see the variable in the path, 1, 2, 5, 8, 1, 2, 5, 8. So each column is encoded by such paths. And to say that the paths are non-crossing, non-intersecting, is equivalent to say that each row is weakly increasing. See, for example, I have 1, 3, 1, 3. Suppose I was going to go, so I will put a 4 here. And if I have 4, this is 1. Yes, I should put 4 here, and this would be decreasing. If I was going, this path was going here, touching this one, then I should have a 4 here for the column 1, 3, 4, and then this would be violating the condition that this would be the weakly increasing. So everywhere there is always two ways to encode Young tableau or semi-standard Young tableau by path. If you read by column or by row, so there is a certain duality between row and column. So there is a duality in a Jacobi true D and true D Jacobi. There is two identities. And the duality is between homogeneous symmetric function and elementary symmetric function. Now you can easily extend this to skew-sure function. Skew-sure function, instead of taking a partition, you take a difference of two Ferrer diagrams. So everything is the same. The skew-sure function is the sum of the weight of such a skew diagram. So semi-standard skew tableau in increasing weakly in row and increasing strictly in column. So the skew-sure function is the sum over all possible weight of all possible skew. And then you have analog. I go a little fast. You can imagine there is an analog of Jacobi true D for this function. What is changing is just instead of having consecutive point, starting point, the starting point maybe are not consecutive. So the starting point and ending point are encoded by the two. Ending point was encoded by the blue, the upper border of the diagram. Now the starting point are encoded by the lower border of the tableau. So we have the same kind of thing and dual identity with the skew-sure function. And again, you have the interpretation. The starting point are not consecutive, ending point are not consecutive. So each starting and ending point are defined by the two partitions. So I give you this extension because I like to put these two configurations of paths. I like to put them together. You see, you put the red path, the red configuration on the blue configuration. And this is a beautiful example of what can be called the duality of path or duality of configuration. So you see each blue step of one configuration, its bijection is a red step of the other configuration.
bijection between configurations
Yes.
of two types.
Yes. There is a bijection from this to this. Because you can always, from this, go to the standard, semi-standard Young tableau, so skew Young tableau, take the read by row, by column, and then you get back this. But the direct bijection is you take the blue configuration, you put each blue step, you associate a vertical red step, you extend the path by in a unique way, and you get a dual configuration. I put it because in the next class.
But how do we figure out where it ends? The A, suppose we have the red path.
It's almost.
So how do we figure out?
No, they are just. It's the same. There is some hole here.
Yeah.
It's exactly, but you are just. It's shifted by half. It's exactly the blue are exactly filling the hole here, and the red, see, the blue are filling the hole here. It's just there is just a shift. So that the vertical and horizontal step exactly in correspondence. But it's exactly you get exactly the sequence of red is exactly the whole of the sequence of blue. So this gives you the idea of duality. I will not make precise statement what is the dual of a path, but just to give you a flavor of this idea, the idea of duality. Duality in path. We have a duality in a standard, in a Young tableau, but duality in path. So this is the idea of the duality in path. You have here a determinant, as you see, with a very compact configuration. Like, you remember the Fermat matrix, determinant was 1. It was all the paths were so close together. So suppose my path is very close together. This is a determinant equal to 1. And then suppose one of these paths, you take off, you delete this, so you make a hole in this spider net. So making a hole is going to propagate inside the network, and the propagation of this hole gives you the dual path. This is a rough idea. So here you have some paths, and here the dual paths, which are more or less vertical. You have the two configurations dual each other. So let's go back to the homogeneous symmetric function. If suppose all the ending point and starting point were all consecutive, then there would be only one configuration. Suppose they're all consecutive, then there should be. But here I have put a hole. So this make a propagation. The hole is going to propagate in the initial completely packed configuration and propagate until here. So the propagation of the hole is encoded by a path, which is a dual path. And you recognize the path of the homogeneous symmetric function and the path of the elementary symmetric function. And then you have not only you have the dual of a path, but you have a dual of a configuration. So let's apply this to this very compact configuration giving a determinant equal to 1. So exercise, prove that the term ij of the inverse matrix is this. Minus 1 power I plus j, sigma over k of binomial coefficient k choose I, binomial coefficient k choose j. I claim that the proof can be done by using this idea of a dual path. So let's take a hole. Taking the cofactor, you delete the row number I and column number j. So deleting row and column means you are putting a hole here and putting a hole here. And the hole propagate in this configuration. And the propagation, then the two propagation is going to meet exactly on the diagonal. And then they go together with the green path. So the red path is this. The blue path is this. The k is exactly the starting point of the green path. This is our inverse matrix in Bordeaux. So exercise, put this in, convince yourself that you get the right formula for the inverse matrix. Now again, application of path duality for a problem related to physics, the TASEP. So if you remember in the previous complementary lecture, the TASEP was this model in physics. When particles are moving in a strip, all particles go from left to right, and in each cell there is at most one particle, and they can enter the cell, the strip, they can go out, and then they can only move from left to right. And then there is a so-called stationary probability in the Markov chain theory, and then there was a combinatorial interpretation of the stationary probability was exactly equal. When you have a state like this, full, to each state you associate a green path. So the first cell, so you have a red point, then the empty cell. The cell, these two cells is here, and then empty. So you have this green path associated to this word. And then I claim that stationary probability is exactly the number of blue paths, number of paths below the green. They can touch, but they never go above the green path, starting at the same point, ending at the same point. And to get the probability, you have to take the summation of all possible pair of paths, which we know is a Catalan number Cn plus 1, so you divide by Catalan number, and you get a nice probability. So now the combinatorists will say, but what is the number? You fix the path omega. What is the number of such blue paths? And then there is a nice formula, which go back to, sometimes it's called Narayana or Krivera's determinant, but it go back to McMahon. McMahon gave a formula for the number of, now we have changed the notation, the number of red paths below the fixed blue path, which means the number of Ferrer diagram which are included below a fixed Ferrer diagram in the Young lattice. And then there is a nice formula, which is this. It's a determinant of some binomial coefficient, which depends of the, here is the example of a lambda. It's a partition with maybe some 0. So you see the partition lambda is 0, 0, then there is 3, 5, 5. It's a number of cells in each of this row. So I have a partition to the blue path, and to this partition I associate this determinant. And I claim, by taking the dual path, the red configuration of paths, you have the green paths are the dual path, and here is the dual configuration. The green path is the dual path of the red path. I claim that this determinant, if you fix the starting point to be this point here, ending point to be this point on the path, I claim that the number of paths going from this any starting point in yellow to any ending point in orange, I claim that this such number is exactly this binomial coefficient. See the path, each path have only, they can go east or go the diagonal northeast. So this is the proof. By using again the idea of duality, you are counting to a single red path. This single red path is going to be in bijection with the whole configuration of green paths. See, now the bijection is obvious on this picture because when you have the red path, on each of these points, take each vertical step, and you put a 45-degree green step. Take the green path, so these 3 vertical steps. Now this vertical step, you put a 45-degree diagonal step. For this vertical step, it's the same. And once you have this green step, there's only one way to connect them to get a green path. So you can check that the number of such paths for I equal j is binomial coefficient lambda I plus 1 plane 1. So exactly lambda I plus 1. Number of such paths is exactly lambda I plus 1. The number of parts here, for example, I have 4 cells, and number of such paths here is 5. 1, 2, 3, 4, 5. So it's exactly lambda 4 plus 1. Now you can check that if you move the ending point by 1 step, or you move by 1 step here, then you will have this. The number of such paths is going to be exactly this. So I have a bijection between the red path and the configuration of dual paths of the green path, and this bijection, this configuration of uncrossing green paths, give me the determinant. But if you well remember, the TASEP was with 2 parameters. alpha and beta, the probability to get in and to get outside. So the TASEP was interpreted as a sum, if you well remember, the sum of the weight of all overall binary tree with alpha power the length of the left branch, beta power the length of the right branch. And this interpretation gives you a perfect symmetry between alpha and beta when you reverse the process. And we have seen that the binary tree, the given canopy, are in bijection with such a pair of paths, which give you the two possible interpretations of the TASEP. But now if you try to transport the alpha beta on this, then there is you lose the symmetry, but you can put the two parameter alpha beta in this pair of paths. And you can get a determinant. So this has been done by a young student in Berkeley. She has done analog of alpha beta, so she gets this determinant. So an extension of the McMahon-Creveras-Narena determinant with two parameters, alpha and beta, and the symmetry is lost, but at least, and she gave a bijective proof in a recent paper on arXiv for this formula, giving, so you have an explicit formula as a determinant for the stationary probability of the TASEP model with two parameters alpha beta. And she gave a bijective proof of this, again using the duality of paths. So, difficult exercise. There is an extension. Instead of taking the number of paths below a given path, Creveras has given you take two partitions, the red and the blue, lambda and mu, and you want to know how many seconds of paths, or how many seconds of Fourier diagram with a certain number of terms, with R terms, which are between the blue and the red. So it's like in a Young lattice. In the Young lattice, I am taking an interval of Young lattice. I want to count the number of chains of given length in this Young lattice. So we get a nice determinant. And there is a similar proof, again, with a dual configuration. This configuration of paths is going to be in bijection with the configuration of the green path, but you have to extend the. So I leave you as an exercise to try to find the good configuration, the good dual configuration, giving this determinant.
So what is R?
Or the number of paths. It's
The parameter is just a number.
there is the length of the chain, the number of paths between the two. So if I put R equal 1 and all the mu equals 0, R equal all the mu equals 0, I should get back this. So this is an extension with this is I think the original Creveras 30 or 40 years ago. Now another application of the LGV lemma. So you remember we have done an excursion, small excursion in the world of orthogonal polynomial. So I just remind you, orthogonal polynomial, formal orthogonal polynomial, they are orthogonal for a linear functional f. I remind you what this was, chapter 3C, I think. No, 4C with Laguerre history. So this is the formal definition of orthogonal polynomial, and you remember that the Favart theorem, I just remind you this complement, that the sequence of polynomial is orthogonal if and only if there exists two sequences bk lambda k of coefficient, such that the polynomial, the sequence of orthogonal polynomial satisfies this three-term linear recurrence relation. So if your polynomial are orthogonal, if there exists a certain f for which they are orthogonal, then they satisfy this three-term recurrence relation. And conversely, if you have a sequence of polynomial satisfying this three-term recurrence relation, then they are orthogonal for something. And one of the main theorems was to say that if they are orthogonal, if they satisfy the three-term recurrence relation, then they are orthogonal for linear functional f, which is defined by the moment. And the moment is going to be the sum of the weight of all the Motzkin paths of length n. With this weight, I just remind you, the weight of the Motzkin path is 1 when I go up, bk when I am at level k, and lambda k when I go down, starting at level k. And then the weight of the path is the product of all this weight. So here I have b0, b1 to the square, lambda 1 to the square, lambda 2. And I claim that the sum of all the weight of all the Motzkin's paths of length n give me exactly the moment of this polynomial, which satisfies this 3-term recurrence relation. So if you know the polynomial, there is three things: the polynomial, sequence polynomial, the moment, and the bk lambda k. So any of the knowledge of one of these three things give you the two others. So of course, if you have the bk lambda k, then you get the moment. Now if I have the moment, how to get back the bk lambda k? And this is the purpose of this computing the lambda k bk, the bk lambda k. So there is some classical formula. There is some algorithm efficient, but there is an explicit formula, which the explicit formula, they are very classical in numerical analysis. They involve the so-called Hankel determinant. So what is a Hankel determinant? The big Hankel matrix is this. You have a sequence mu n of moment or anything. So you take the matrix, the term ij is mu index I plus j, starting at mu 0. And the Hankel determinant is any minor of this matrix. I claim that I can interpret any Hankel determinant by, I am in the case by, there are two cases. If I take Dick path with bk equals 0, or Motzkin path when bk may be non-zero. So suppose bk equals 0, you have only Dick path, weighted Dick path. So I suppose that mu n is the sum of the weight of all Dick paths of length 2n. I have only the lambda k. It's here. Suppose bk equals 0 to simplify. I have only 1 and bk. So I have only Dick path. The moment mu n is going to be the sum of the weight of all the Motzkin paths, all the Dick paths of length 2n. So suppose I have mu n as a sum of weight of Dick paths, and I claim that this Hankel determinant, for example, is exactly the sum of the weight of all such configuration. So you see A1, the blue points go from left to right. The red points go from, no, the blue points from right to left. The red points go from left to right. And look between A1 and B1. See the sum, A1, B1 should be mu 3, the sum of the weight of all the Dick paths of length 6. So mu 3 is this. So I have put the blue points in a certain way so that I have the column 3, so that all these points here, mu 3, the blue point in a certain way, the red point in a certain way, so that I get exactly the sum of the weight of the path going from AI to Bj is going to be exactly mu index I plus j for a certain, for example, mu 8 is the sum of the paths going from A2 to B2. Mu 8 is going, this give a path of length 8. Now if I take from A2 to B3, A2 to B3 is mu 11, I am increasing by 3. So you can check that taking any minor of the Hankel matrix, so you have a given, taking a minor of the Hankel matrix, you are giving a certain index of row, a certain index of column, and I claim that giving the index of row in column is exactly giving the blue point and giving the red point. So that if I take any AI going to Bj, this is going to give me mu index I plus j. So just check by yourself that taking a minor of such matrix, as soon as mu n is the sum of the weight of all Dick paths of length 2n, then I get exactly the determinant interpreted by the sum of the weight of all such configuration. And for Dick paths, if you have only Dick paths, then the crossing condition is satisfied, and then I can apply the lemma. Now for Motzkin paths, the crossing condition is not satisfied. So maybe some, see like this, some virtual crossing. So I call this virtual crossing when the two paths, they seem to cross, but there is no common vertex. So for Motzkin path, I should apply the lemma in the general form, where there is still some plus and minus term, there is some -1 number inversion. But if you take the following Hankel determinant, delta n equal completely packed, mu0, mu1, mu2, mu_n. So you take the first n column and the first n row. The minor is a principal minor. All the columns are consecutive. All the rows are consecutive. I claim that this determinant is interpreted by this in terms of Motzkin path. Even if the non-crossing crossing condition is not satisfied, you can do as if it was satisfied, because it's so close, so packed that there is no room to make a virtual crossing. Even if the crossing condition is not satisfied, I don't have any virtual crossing, so I can apply as if it was the lemma with the crossing condition. So this Hankel determinant is called delta n, is interpreted by this unique configuration. So I have delta n divided by delta n minus 1 is this configuration divided by the smallest configuration, and this gives me this path. Now I divide this by the same with shifted by 1, and I get this. And this is a very classical formula that lambda n is the B rapport, the B ratio of is this ratio divided by the same shifted by 1. So it's involved a product of two Hankel determinants divided by Hankel determinant. BK, yes, next slide. But here, what is very important, the Hankel determinant. If one of them is 0, then you have problem. This means there is no orthogonal polynomial. This is a condition when you take a second lambda k. To get orthogonal polynomial, all the lambda k must be non-zero. And when you have a numerical analysis, you want really to compute the lambda k. So this is equivalent to expand the power theory into continuous fraction. If you want really to compute, if the delta n are very small, then the algorithm is not stable because of the division everywhere. Of course, we are not going to make the computation with this. This is explicit formula, but there is some nice algorithm which is called the QD algorithm, the quotient difference algorithm. It is well known in numerical analysis. And this algorithm maybe is not stable because sometimes you divide something very small. So what are the BK? So just again make a hole in this completely packed configuration, delete one of the ending point, and take this. So again, I claim that in this Hankel determinant, so I say I have this configuration of point, the starting point and ending point is going to be associated to a certain determinant which is called key n. Sorry for the call, it's all transparencies, and I will reduce them in the definite version of the slide. So this is called key n. It's an Hankel determinant. You take this first n row and this first n plus 1 row, but the one is shifted by 1. The first column, and then the last column you shift by 1. So such configuration, again, there is no virtual crossing. I can apply the lemma as if it was with a crossing condition. There is no inversion involved. And such configuration, now there is a choice of this path. BK can be at any level. So this determinant, the determinant associated to this minor with the blue and red point, is a sum of all this configuration. So you get this determinant is the sum over k of BK. If you delete BK, what remains is exactly the previous delta n. And so you get this formula. Bn is the ratio of these two Hankel determinant minus this Hankel determinant. So this is very classical formula in pas des approximant theory, numerical analysis, but we get them completely geometrically. So sorry, I have not stated what is the Hankel determinant related to this. What is key n? It's the same as delta n, the first column, first row, except the last column you shift by 1. You don't take it, you take the next one, which gives you this configuration of starting and ending point. Now I finish with determinant, non-crossing path, symmetric function, Jacobi, and we go to tiling. So there's many problems in tiling. Can you tile your bathroom with this kind of tile as I've done Cooperberg? This is Cooperberg bathroom. It's there is Penrose tiling. There is some. So we are not going to work with existential possibility of tile the whole plane. We just want to count elementary tiling like this one. Take tiling of a chessboard. You have a chessboard and you tile it with blue and red dimers, vertical, horizontal dimers, and then everybody knows there is 12 million and something way to tile the chessboard with such dimers. Of course, this is not interesting. You want a formula for any size n by m. If you take any rectangle, and here is a nice formula. The number, I claim the number of tilings of with dimers of an m by n rectangle is 4 power mn multiplied by all this cosinus square. This was a Castellin physicist in 61. This was related to the Ising model. And as you can check, this is an integer. In the case of the chessboard, this gives you the 12 million something. So this formula is terrible for combinatorics. For doing bijection, it's a terrible formula. Example, if you take a 4 by 6 rectangle, so m equal 2, n equal 3, because it was dividing by 2. It depends on how the parity of the parity of m and n. So in that case, 4 by 6, I have this in this formula. There is 6 terms, which are this plus all these terms. You see, you have to divide the circle in 5, divide in 7, take all the cosinus of all this, and you have 6 terms. This plus this, this plus this. You multiply all this like this, and you find 281. If you do this by computer, then maybe you will find 281,000,000. But if you make a high precision computer, then you will get the smallest integer to the real number you will get by computer. So it's a kind of formula that you have to see once in your life, such a formula. So I'm not going to prove anything about this formula, but exercise. If you take 2 rectangles with 2 rows, this is Fibonacci numbers. Very easy. The solution is in the picture. Fibonacci. Pingala. So instead of taking tiling in a rectangle with dimers, I will take tiling on a triangular lattice. Well, it's much better. So a triangular lattice, you see, and I take a kind of hexagon with parameter A, B, C. It's a kind, it's not an hexagon. We see you have 3 parameters, A, B, C, and this distance is equal same like this. This the same as this, and C and C. So I have an hexagon, and I have a tiling, possible tiling, with 3 kind of pieces. Sometimes I call calisson in French. It's a kind of cake near Marseille. There is a calisson. This is the shape of the cake, and there is there is same shape but 3 possible orientation. So you have three kind of tiles: the yellow, the green, the red. When the middle edge is horizontal or diagonal or like this. So here is a possible tiling, and I am asking how many such tiling you can get. Is there a formula for this? Depending on A, B, C. So exercise some. If A equal 1, then I get 2 chosen. So exercise, find a bijection with bilateral dig path. Now if I cut this part, you guess that is going to be the Catalan number. This is 2 chosen, this is Catalan number. So again, find a bijection with dig path. Without looking the result in general case, without applying the formula, but try directly. It's again easy exercise. A little 1 minus was Fibonacci, 1 plus the difficulty of this exercise. Now the general case. Okay, I can put my tiling like this. And what do you see? You see a 3D Ferrari diagram. In fact, tiling is exactly in perspective of here maybe you don't see very well the partition, but if I write like this, then you see really the partition. So in fact, tiling of the hexagonal lattice is exactly counting 3D Ferrier diagram or counting plane partition. So tiling on an hexagonal ABC is exactly counting plane partition in a box. So this is McMahon formula we have seen last time. And so the number of such tiling with calisson is exactly given by this nice formula. In fact, tiling is the same thing as perfect matching. Tiling with this kind of things. What is the perfect matching? We have seen the matching polynomial of a graph in previous lecture. And the constant term of the matching polynomial is exactly the total number of perfect matching, means all the edges are covering the graph. They are 2 by 2 disjoint and there is no isolated point. So here is my hexagonal, my triangular lattice, and in green the dual graph, which now is a hexagonal lattice. So when you have a tiling with 3 kinds of calisson, you can associate bijectively a matching of this dual graph. For each tile, you put an edge between these 2 vertex, which are the center of each face, each triangle. Here you put an edge between the vertex, which are the center of these 2 triangles in green. So the tiling becomes a perfect matching of this graph. It's the same of this hexagonal graph. So the number of perfect matching is going to be exactly given by, again, McMahon formula. Yes? So you have a kind of a perfect matching for such tiles. There is not every perfect matching in any graph, but for such example, not taking into account tableau, there is many bijection between all this. So the LG lemma, I was talking in chemistry, some people they are interested in matching in the benzoin molecule, so they are working perfect matching, and they do some bijection between this matching and the path, and they get the idea of a non-crossing path and a determinant. So this comes also from chemistry, the idea of determinant and the non-crossing path and counting perfect matching. Now we come to a most beautiful tiling, the Aztec tiling. It's many papers on this tiling. So Aztec tiling, this is the Aztec diagram. So why it is Aztec diagram? Because if you look above, you have like an Aztec pyramid, and there is a lake in front of the pyramid where the pyramid is reflected in the water, and you get the Aztec diagram. And here we are going to tile the Aztec diagram, like for the chessboard, like for rectangle, but with dimers, horizontal and vertical dimers. So you take the chessboard, you just turn 45 degrees, and you get a kind of another chessboard, and you tile the chessboard. So what is the number of such tiling? And now there is a very beautiful formula. It's 2 power 1 plus 2 plus etc. n, which is 2 power n plus 1 over 2. So this was in the paper by Elkis, Cooperberg-Larson in 1992. So we see from the formula, ugly formula with cosinus, sinus in the rectangle, you get now a very beautiful formula of 2 power something. It's a power of 2. So here is an example. Again, tiling of the Aztec diagram is equivalent to perfect matching of the dual graph. So I am also counting this. It's the same. And now I give you a proof of the formula 2 power something. A bijective proof without any calculus. Which is, as soon as you have a determinant, usually you finish with calculus, maybe terrible calculus, or maybe not so terrible, or maybe easy, but here I will give you a proof without any calculus. A bijective proof. Some people have given, there is many papers on this. Some people have given bijective proof, but there is you have to do a lot of things. There is non-crossing coefficient of path, and you have to work on this, etc. But I give you, this proof I am going to give you is new. To my knowledge, it does not appear in the literature. It's just an application of everything we have done before. So first we are going to encode such things with path. So here is a bijection. I have a bijection between Aztec tiling and the configuration of green paths. So the green paths, they can go up. There is a level, but the level, you see, it's not a level like in the Motzkin path. It's counting double the level. It's like Motzkin path. Each time you have a level, it's count. You have to repeat twice the level, and then you can go down. Now the rule is the following: you put the starting point of the path. You just take the portion of the diagram below my axis here. Take this point, and then this point, this point. Here the ending points are this point, this point, this point. So the last point is the. And then the rule is the following. Each time you start from the ending point, each time you cross a vertical diamond, you go up until the other edges of the vertical diamond on the upper part. When you are following a diamond horizontal, then you continue the diamond. So I reach a vertical diamond, so okay, I go from this point, I cross the diamond like this to go to this point. Now I am again a vertical diamond, so the rule again is you go from one side of the diamond to the other side by making it can be a northeast step or a southeast step. So there is only one way, starting from this point, you have only one way to define the path. Each time you meet a horizontal diamond, you go horizontally. Each time you meet a vertical diamond, you go from one edge to the other edge of the vertical diamond by crossing maybe northeast or maybe southeast. So there's only one way. And at the end, you finish with this. And I claim that what you get is a non-crossing, non-intersecting configuration of paths. And second claim, this configuration is in bijection with the tiling. I leave you this as an exercise. Okay, so now I have to work with this, but to have a nice determinant, we have seen Hankel determinant, which seems to have a nice property with orthogonal polynomial. So let's make the whole diagram to get some dict paths. And you can see that if I extend the path like this, with the blue edges, the new configuration of path, blue and green edges, is in bijection with the previous configuration. This is equivalent to count this configuration. So see now I have a kind of Hankel determinant. I have a configuration exactly the same as I was working with orthogonal polynomial. So here as the starting point, A1, A2, A3, ending point B1, B2, B3. So such paths, you see such paths, they are called Schroeder paths. You are on the grid lattice of the dict path, and you can go at the level, but the level is counting double, not like Motzkin paths. So such paths are counting Schroeder paths. They are counted by Schroeder numbers. So I claim that the number of such configuration of paths is exactly this Hankel determinant. So the first Schroeder number is 2, 6, 22, 92, and 394. This is the sequence of Schroeder numbers. So look here, between A1 and B1, there is only two paths. There is this dict path and the level path. Between A2 and B2, there is 22 Schroeder paths. Between A3 and B3, there is 394 Schroeder paths. And then you can check that because of the Hankel property, all the other coefficients are exactly the coefficient ij is the Schroeder index I plus j. Where Schroeder and this n, Sn, is the number of Schroeder paths of length. So the length is because if I take the length of this, it's 5 as a path, but if I take the length of this, it's going to be 6. So Sn is not counting the number of Schroeder paths of length n, it's counting the number of Schroeder paths going from a certain point to n, from 0, 0 to n. Like dict paths, think of dict paths, they go from 0, 0 to the point 2n, 2n and 0, and if I allow the level, then I get the Schroeder number. Schroeder number is analog of, we have seen Catalan, we have seen Motkin, now Schroeder. See the trilogy, the same family, they are more or less the algebraic genetic function. Let's exercise, find the algebraic genetic function of this, and they are more or less the same family and a little more complicated. So now if I take the determinant of this Schroeder Hankel determinant, then I get this, which is equal to 2 power 3. If I get the 3 by 3, if you make really the computation I have done for you, so the 6 term, this minus this, which is 64. So by which miracle you get this? So believe me, I am going to prove this without any calculus. Just apply what we have done in the previous chapter. I'm really thinking to try to get the proof. So bijective computation, bijective proof of the Hankel determinant to show that it's a 2 power something. So the Schroeder number, it's the number of such paths, and the determinant is going to give me the number of tiling of the stack diagram, which is a power of 2. So here is a Schroeder path. But what you can do, you see, it's Schroeder path. You can change this to this. Or maybe you can change this to this. Or you can change this to this. So any Schroeder path is obtained from a Dicke path by maybe you make the peak invariant, or maybe you cut the peak. So for a given Dicke path, you have many Schroeder paths, which is 2 power the number of peak. Okay, so Sn, Schroeder number of such paths, is the sum of all Dicke paths of 2 power the number of peak. Schroeder path is a colored Dicke path. You put a color on the peak, blue or red, if you keep the peak or if you cut it. So, easy, huh? So now we know that counting Dicke paths is a beta distribution. This is an area number. But even I don't need the formula for an area number. I promise you to give a proof without any calculus. So I don't need this. But staircase polygon, the number, the beta distribution, it was the staircase polygon according to the number of columns. We have seen the bijection. The beta distribution, counting Dicke paths by number of peak, is exactly counting staircase polygon by number of columns. Now we have seen another bijection sending you to 2-column Motkin path. Remember, we are looking like this, and the width between the 2 cut, the 2 paths is variation is given by this. Now the 2-column Motkin path, we transform this into a Dicke path. And now the beta distribution was becoming the number of edges in red, which are going from an odd level to an even level. So here, you see, you have 5 such, and then so there is a bijection. So the distribution of Dicke paths according to the number of peak is the same distribution of Dicke paths according to the number of time you go down from an odd level to an even level. So I can write the same. Schroeder number is the sum of the weight of all Dicke paths of length 2n, and the weight is going to be 1 when I go up, and lambda k equal, as for Favart theorem or Taylor polynomial, lambda k equal 1 if k is even, equal 2 if k is odd. So I have to take the Hankel determinant of this. Not of this interpretation. Hankel determinant is equal to this. Exactly as before, where the gamma is, I have changed the notation. The mu is exactly the sum. The mu n is the sum of the weight of all such Dicke paths. So the mu n is a Schroeder number in that case. And the lambda k is this weight, which I call now gamma. This comes from another slide from the orthogonal polynomial theory. So this is considered this is the mu n, the sum, the Schroeder number, the sum of the weight of all Schroeder paths. And now you have to put the gamma, this valuation lambda k equal 1 or 2. So the valuation is this. Now there is only one coefficient of path, And the weight is 2 power, 1 plus 2 plus 3 plus 4, which is this. So I get the proof without doing any calculus. See, the magic of a... But you have to know all bijection, everything. And I apply twice the LGV lemma. First time to get the Hankel determinant of Schrödinger number. Second time to get this new Hankel. But now there is only one configuration. And I transform my problem where there was many configuration non-crossing Schrödinger path. There was many configurations. Now there is a single one. And all the two are put on this unique configuration. So this is a proof that the number of tiling is this. So we speak about the Schrödinger numbers. In fact, there is 2 family of Schrödinger numbers. There is a Schrödinger path 1, 2, 6, 22, 90. This was the number of Schrödinger paths. But there is a little Schrödinger, which is half. 1, 1, 3, 11, 45. This is half of the previous one, and which are counting Schrödinger tree. So what is a Schrödinger tree? Is little Schrödinger. They are counting trees, but they are counting, we have seen a complement about the associahedron. You remember the associahedron? All the vertices were triangulation of regular polygon, or it was binary tree. This is the associahedron with the 14, there was 14 vertices. It's a convex polytope where the vertices are in bijection with binary tree or triangulation, and the edges are the flip in the triangulation, or the edges when you go up in the Tamari lattice. So there was a whole complementary lecture on this. What I have not done is what is the total number of faces of the associahedron. Number of faces, that means here, for example, number of vertices plus number of edges plus number of faces plus the total accessory top, which is 45. In this case, I have with 2 points I have 3. With the 5 Catalan, I have 5 plus 5 plus 1 equal 11. Here they have 45. So 1, 3, 11, 45. Right, it is exactly half of the previous Schrödinger 1, 6, 22 I have in the previous lecture. In the previous with the Aztec diagram, I have this Schrödinger of before. It's only half. So why is the number of faces of the associahedron is half of this Schrödinger number, the number of Schrödinger paths? So the interpretation is, in fact, is little Schrödinger is with trees. So each face of the associahedron is associated to a partial triangulation. In fact, the vertices are triangulation. The edges, when you do a flip, and edges, you delete the edges. So all the edges are, in fact, triangulation when you delete one of the edges. The face are you delete 2 diagonal, etc., etc. So it's a kind of simplicial complex where each face, vertex, hyperface is embedded in the other one. So you have to count the total number of partial triangulation. So partial triangulation, if you have done the exercise, giving there was a video, even the bijection between triangulation, complete triangulation and binary tree. Now if you take a partial triangulation, you get another tree, which is called a Schrödinger tree. It's a tree. So Schrödinger tree, this is the root. So it's a tree where any vertex, there is many child for one vertex. Each vertex has at least 2 child, 2, 3, or 4, and you are counting this tree according to the number of leaves. You are not counting... So you counting such tree for the number of leaves. So it's a planar tree, and each vertex may have many sons, but not a single son. Because you have infinite number of trees with a single son and only 1 leaf. So we are counting trees with at least 2 or 3 or 4 sons in each vertex. It's a total order of the son, and you are counting this tree according to the number of leaves. So this is in bijection with the faces of the associahedron, and this is another interpretation of the Schrödinger numbers. So I'll leave you at an exercise that this kind of trees are half of the number of Schrödinger paths. I will not explain why, but the two are one is half of the other. But now, look at this number, 1,000 trees. This is called Hipparchus number. So this goes back 2,000 years, more than 2,000 years ago. So what is this number? What Hipparchus is? Hipparchus was not counting number of faces of the associahedron. So it was related by Plutarch. That Chrysippus says that number of compound proposition. that can be made from only 10 simple propositions exceed 1 million. And Hipparchus says, no, the number is exactly this. So during many years, in the last century, philosophers, logicians, they tried to understand what Plutarch was counting. And then a young American in 1994, David Hughes, he looked at the Encyclopedia of Sequence, and he found this number. In 1 second, this second was a Schroeder number. Schroeder number counting trees. So we are sure that Hipparchus was counting this kind of trees. What is the relation between trees and making composed proposition from simple proposition? The relation is the following. You see, when you have your trees coming from the face of the Pascal of the associaedron, you know that trees are related to parentheses. Dict path, binary tree is a dict path, parentheses, and if you have this general kind of trees, they are related to general parentheses. You have some variable, and you put some parentheses, but between two parentheses, maybe there is several blocks or several variables. And it's sure that this is exactly what they are counting. This is a simple proposition, and this is a composed proposition. So Hipparchus was counting this. It's sure. Because we lost almost everything from Hipparchus. We just what was not lost was this number. So from one number, you can completely reconstruct the history. Now you have to exercise, try to repeat what was doing Hipparchus at that time. Don't make the list of the 100,000. Try it by yourself without knowing nothing, without knowing it's algebraic genetic function. If you know it's algebraic, you take the derivative, you take the p recursion relation, you have the relation. So try to get the relation. There is different recurrence relation. So if you take the most obvious relation, it's analog to Catalan, but instead of having two terms, there is many terms. So you can have a recurrence relation. Then you are going to take in terms the number of composition of integer. And composition, there is a partition if you make a commutative of the parts. So you are going to count for each Ferrier diagram. You are going to have certain numbers. So I'm sure he was maybe making the picture of a Ferrier diagram. Each Ferrier, there is some composition, there is some numbers appearing in the recurrence, and maybe it's a special case of Catalan numbers. When you have only binary things, maybe it was also. Maybe he has a Catalan number also behind this. We don't know. You can imagine many things from a single numbers we found in the Encyclopedia of Sloan. But I won't have the pleasure to go back to the rectangle, this terrible formula. Finally, it's not so terrible. Because we know that a tiling of the Aztec is in bijection with configuration of paths. So tiling of a rectangle, like this, again, do exactly the same technique. You put your starting point 2 by 2, this, no, etc. And you follow the same thing. When you cross a vertical diamonds, you just go 45 degrees up or down. If you follow, so we claim that this is in bijection with a non-crossing path. So you have to count such configuration of non-crossing paths. And this what I have been done by Volker Strel. And in fact, it is proof. It's a long proof. There is several bijective tools to use. And it shows that, in fact, this terrible formula, you recognize the zero of Chebyshev. Go back to chapter 1 or 2. There is a zero of Chebyshev involved in this. So there is a Fibonacci. Chebyshev was a matching polynomial of a. This is a related to the matching polynomial of a graph with m and n. It's exactly the matching of each of the size. You have matching of m and n, maybe m over 2, n over 2. There is a parity is involved. So you have a kind of matching of two polynomials indexed by the length and the width of the rectangle. And you have to show that this formula, in fact, is a resultant of more or less some modified this kind of polynomial. And he gave a proof, a bijective proof, but he used some other techniques. A path is in bijection with a heaps of cycle, so he used a heap theory, which we will do in another class. So you don't have all the tools to prove this nicely without too much calculus. But there exists a very nice proof of this using bijective rule. There is some calculus, few calculus to do, But it's mainly the two Chebyshev. The Chebyshev index by M and N are involved in the story, and the zero appear as a resultant. Another complement, now we go to probability. The Arctic, the very well-known, famous Arctic circle theorem. So once you have a bijection, the formula for the number of tiling of the state diagram is 2 power something. There is another proof by Prop and his co-author, a bijective proof. If you have a tiling of the diagram of size n, then the tiling of a diagram of size n plus 1, the number of such tiling is 2 power n multiplied by the number of tiling in the previous diagram. Each time you multiply by 2 power n the number of tiling. So if you know a random tiling on a diagram of size n, you take a random word of length with 2 letters of length n plus 1. The pair of this must be in bijection with the tiling of the diagram n plus 1. So if the first is random word, then you get a random tiling. So by increasing the size, repeating the bijection, you can get a random tiling. So this is experimental combinatorics. This gives a bijective proof of the formula, directly bijective proof with a cascade of bijection. This is called the shuffle domino shuffling. So here is what you get when you get a random. With random means the equidistribution. All the tiling have the same probability. So there's 4 colors. I will explain the 4 colors. So this is a random tiling of the diagram is size 50. The number of such tiling is 2 power 1,275. It's beginning to be big. And this is a random tiling. So you can see some regularity appearing. So what is the rule to get the color? So when you have a tiling like this, you put black and white coloring of the cell, the same as for the chessboard. Now there's 2 kinds of horizontal dimers. When the black cell is on the left, black cell on the right, so you put these colors. Again, there is 2 kinds of vertical dimers, according to the color black and white. So you put this color. So you have 4 possible different kinds of dimers, 4 possible colors. And in that case, so this gives me the rule to get the colors of the. So see here, it's always yellow here. The 4 color, if if the dimer is horizontal, it's always yellow. But then in the middle, there is no precise rule. So here is the random. So see the algorithm. This comes from called domino shuffling. You suppose you have a random. You suppose this is a bijection. You suppose you have a tiling of this diagram and a tiling of the bigger diagram. This tiling is in bijection with this and a certain word of length 3 with letters 0 and 1. So the domino, the bijection is there is some movement. The dimers are going to move. I'm not going to explain it, but there is a bijection. In the original paper of the Prop and its co-author, there is a domino shuffling which gives you the bijection. So if you repeat the bijection, you can get very easily random tiling, and this is the algorithm. You see, each time you do the bijection, and this is. So unfortunately, I took this from this website in Image des mathématiques in French. Shuffling of dimers is 2H domino, and unfortunately, the colors are not the same. I don't understand why. There was a 4 color, and when I just put on my software keynote this, and the color is changed, and now a bigger one. So this is a circle slowly appearing. And this is much bigger. And you can see with your eyes what is the circle Arctic theorem. And when you take in the middle, inside, then the probability, if you take any random dimers here, probability to get one of the 4 colors is exactly 1 over 4. You can get any color here. And then here, the probability is 1 to get a red. On the corner, it's 1. And the limit, you can imagine what is the theorem. When you are close to the circle, then the probability suddenly becomes 1. Here is not 1/4, but it's here is really 1/4 for everybody. And when you are coming here, there is a kind of phase transition in physics. Suddenly the probability change, and this is frozen area. Frozen, everybody is frozen. This is a gas. This is frozen. This is why it's called the Arctic Circle, because here it's very cold or very hot. No, here is hot, and all this is very cold. So you can imagine what is the Arctic from just your. So this is really experimental combinatorics. You can guess the theorem, and from using by Prop told me that it was using the bijection that he realized that there was this very nice Arctic Circle proposition. Now in the case of a chessboard, there is nothing like this. For the rectangle, it's normal the formula is ugly, so yeah, for nice formula you have nice phenomena. For a formula like a rectangle you have this. It's a gas everywhere. So I will finish with some, I cannot finish this class without perfect matching also. There is a Pfaffian methodology, so this is just a complement. Enumerating perfect matching on a graph, there is a Pfaffian methodology for planar graph, and this was introduced for the Ising model by Castellin, Fisher, Temperley in the 60s, so about 50 years ago. The Ising model, it's equivalent to count, you have to count such a picture, you have a finite rectangle, and they call this closed graph. So it's a graph with the green edges. In any point, there is no edges, or maybe 2 edges, or maybe 4 edges. And the number of edges going to any vertex is even 0, 2, or 4, and you have to count such picture according to the number of green edges. Total number of green edges, this is more or less solving the Ising model. And then there is a Pfaffian methodology. So Pfaffian is more or less intuitively the half of a determinant. Determinant is summing over all permutation. Pfaffian is summing over all involution with no fixed point. The Pfaffian of a certain tableau, half of the tableau, like this, Aij. Then the Pfaffian is the sum over all involution with no fixed point. The product over all the chord, like a chord diagram, you make for a product of all the chord, A index this, -1 number of crossing. So we have seen involution with no fixed point, there's a number of crossing, and then you take the product alpha equal j, sorry for the change of notation. So this would be the term A16 in the tableau, this would be the term A47, etc. So Pfaffian is the sum of all involution with no fixed point. There is a -1, the number of inversion is replaced by number of crossing. And then for a skew-symmetric matrix, if you have only half of the tableau, you can make the whole tableau by putting Aij equal -Aga, and then you have the determinant of a matrix, of this skew-symmetric matrix, is the square of the Pfaffian. So Pfaffian calculus can be reduced to determinant calculus. And then the Pfaffian methodology, you take a graph, vertices at 1 to k, and you want to count how many perfect matching in the graph. So the idea is to put an orientation on the edges, such as that, then now the incident matrix of the graph, instead of being 0 and 1, it will be 0, 1, or -1. The term ij, if you have in the right direction, you make 1, but if you go in the reverse direction, you put -1. And the idea is, for a matching, you have a certain number of -1, edges in the wrong direction. So this number of -1 must must be the same parity as the -1 coming from the crossing. Because any matching is an involution with no fixed point. So taking the Pfaffian, you have to take -1 power the number of crossing. And if you multiply by -1 the number of edges in the term like this in the wrong direction, you must get 1. So we will call orientation admissible if this is possible. So computing the number of perfect matching, we use the Pfaffian of a certain tableau with 0, 1, and -1. And then Castellin theorem tell you that this is possible for any planar graphs. So this was the way they solve they count perfect matching of certain graphs, which are equivalent to solve the Ising model, to get the partition function of the Ising model by counting some Pfaffian, putting admissible orientation, then getting a Pfaffian, then a determinant, and so you can make the explicit computation. So for example, the Ising model, some of the first paper, you change this green edges, you change, you explode the graph, you replace this by this, and then you change each of this. On each vertex, there is some configuration of the green path, and you change into this. But you see here, this is associated to this. So for a bijective man, you stop here. This is a 1, 2, 3 correspondence. How can you do something explicit? You want explicit formulas with something which is not bijective. It's 1 to 2, 1 to 3. And worse, when the graph you get is not planar. You cannot apply the theorem, the Pfaffian methodology. But people don't care. They apply this with a non-planar graph. When you go to infinity, the genus of the graph go to infinity. So the graph is highly non-planar. It's not one-to-one. And what you get at the end is the exact solution of the Ising model. So by doing this, you make something bad. But taking non-planar, you make a second thing bad, and the two bad things cancel, and you get the right. So this was a kind of miracle. But then the miracle was explained by Fisher, where you get really a one-to-one correspondence. You explode. See, there is many possible situations, and you have a one-to-one correspondence between this configuration and some perfect matching in a planar graph, more complicated. So in conclusion of this class and of this course, a nice formula, the last one. So, Hankel determinant of Catalan number is equal to this nice. Nice means the product divided by a product. So we see we have seen many determinants, plane partition, semi-standard Young tableau, Aztec diagram. Now this Hankel, again, product divided by product. This is the Hankel. It's not easy to see that it's a product. It can be computed by calculus, but not only nice formula, the festival of bijection. So this, you see this, the number of perfect matching of this graph. There is hexagon, pentagon. The number of perfect matching is exactly this Hankel determinant. Why? You do like the Ising-like bijection. From this, you go to this. There is a bijection. You have non-crossing path. It's the analog of exploding the graph. And here you put some dimers in blue. So it's not crossing coefficient of paths, but the starting point can move. So it's a sum of determinant. So you could, or in fact, it's a Pfaffian again. Now do the same kind of bijection. From a non-crossing coefficient of paths, we get a Young tableau. Like this. So it's semi-standard Young tableau, but written in the wrong, the columns are weakly increasing and the rows are strictly increasing. And each column is an even number. So there's bijection, analog the bijection you have seen between path and tableau. Now from tableau, Robinson-Sønstedt. But apply to the case, Knut with repetition of the RSK. Apply in the case of an involution. And we have done the analog of Burge. Burge have a direct bijection. In the case of involution, you can insert the bumping process, 1 point, or a cycle of length 2 at the same time. So that the number of odd column with odd number of cells is exactly the number of fixed points. So here we have all columns are even, Robinson-Sønstedt by the light. Put the light, and you get configuration of Dick path. This is Knut, light with a repetition of points. You get this. From this, you turn and you get a Hankel determinant. And now how to compute this Hankel determinant? You remember, I have talked about the QD algorithm to compute the BK lambda k by the quotient difference algorithm. So there is a way to interpret the QD algorithm and to go from this configuration to a unique configuration. But unique, all the weight now become rational numbers, and the product of this rational number is giving this. So this gives you proof that a whole tableau of this is a festival for the last part. Okay, so the website, this is for the people who are looking at the video. The website of the course is a special website. Everybody has. So the lecture notes of the course are coming, and many thanks to the student writing the note, Sridhar, Varsha, and Ginu. And thank you very much for all of you, student, professor, friend, the video technician, and Matter Science channel. And it's a video, so thank you for the lecture, listening this video. If you have listened to the 17 video until the last one, this is the number, usually the number of the video, and the last one is 2024. It's a power of 2. There is 4 years of classes. Each classes there is 8 weeks, 16 video. Total video will be 64, and we finish with this, and a special thanks to Ambry for the invitation to come here and give this class. And homage to Sarasvati, the deess of the knowledge, science, music, and poetry. So thank you very much.